Assalamu alaikum. Welcome to a lecture on formal specification and verification using Coq Proof Assistant. My name is Dr. Velayat Khan. I'm an assistant professor at Comsets University, Islamabad WA campus. In this lecture, I'm using a Coq Proof Assistant to formally specify and verify simple system of natural numbers, in particular net list and bags. And this library, which is named as list.v here, in this library, two other libraries have been included or imported using require import command. The two libraries are basics and induction. These two libraries are defined according to the books, the first two chapters of the book, Software Foundation. And these libraries, the Coq script defined in are written in these two libraries is compiled, and then they are included here using require import command. In this library list.v, net product and a number of function on net product have been defined, and then net list, which is a list of natural numbers, is defined. This list is given the name net list. This is a special list. It's a not generalized form of list. We will see some generalized form of list examples later on. So this is a list of natural numbers, and some notations, a number of functions and lemmas are defined on net list, and then a type called bag is defined, which is equivalent to the type net list, and then a number of lemmas and other definitions were defined. So I will just continue from this point onward, and will compile till the cursor all the function and definitions. Okay, so we have just defined a few functions. One function is equality Boolean on list, which is the equality defined Boolean equality on the lists. But this function defines that two lists are equal to each other only if they have the same length, and if the corresponding elements at the corresponding positions are the same. For example, in the first list here we have 5, so in the second list we should also have 5, and the second element is 4, so the second element should be 4, and so on and so forth for all the elements. Then the two lists would be considered as equivalent. A list find just search an element in the list. This is another equality Boolean equality function on the two lists, and this it checks if all the elements of the first list are included in the second list. It doesn't consider the length of the two lists if L1 is smaller than L2 and all the elements of L1 are included in L2, then the two list would be considered as equivalent. And here this last function consider the length of the two lists as well. So if the two lists are of the same size, and if all the elements of the first list are included in the second list, then the two lists would be considered as equivalent. So okay, so using the equality Boolean equality on list, we define a theorem that the equality Boolean equality on list is reflexive. So this is a theorem for all list of type net list. We say that true is equal to equality list on LL. So this is equality Boolean equality defined on list gets the same list again and again. So it just compares that a list L with itself, and it says that when a list is compared with itself, it is always equal to itself. So this is called reflexive property. So let me compile the statement of this theorem. It is okay. We can enter into the proof mode, and okay, and use intro to introduce the only one variable above the line. So this line, this one variable would go to the hypothesis. Yes. And then from this point onwards, we use case analysis. That is the main topic of this library. So using case analysis, using the tactic induction, I'm doing case analysis on the inductive construction of the list L. And we get two sub-goals, and one sub-goal the list L as M null, and in the other sub-goal list L as non-null. So let me focus on the first sub-goal. So we can simply simplify the function equality, Boolean equality and list using simplification tactic. And this would give us true on both sides, and we can close this with auto tactic. And similarly, let me focus on the second sub-goal. So when we focus on the second sub-goal, here we have the two arguments of the Boolean equality is non-null lists, which is basically the same list. Okay, so in this situation, we can proceed with list. We have an inductive hypothesis, but we are not in a good position to rewrite this inductive hypothesis, so we can try simplification. After we try simplification, we get that a comparison fn is equal to itself, and from the first appearance we may be sure that yes, it is equivalent to itself, but we have not yet proved it. If we already have a lemma or theorem that shows that for any natural number n, because n is natural number, for any natural number n, if n is always equal to itself, then we shouldn't need to prove it, and we can just rewrite it. One way is to skip this theorem and come outside of this theorem and create a lemma that says that n is equal to itself. Or the other way is that we destruct this equality, Boolean equality, and then we would get two cases where n is equal to n, and the other case that n is not is equal to n. And then we would solve the two sub-goals one by one. And another method is that we just assert that n is always equal to itself. So I would use with this approach, assert n is equal to, and this equal question mark is actually Boolean equality and natural number, and this is true. This is what we believe at this stage, and let me call this hypothesis when proved as hypothesis on equality HEQ. So let me compile this. We would get an additional goal, and actually this is the sub goal now. And when we prove this sub goal, this will be introduced as a hypothesis with name HEQ above the line, and that we would be able to use it in the proof of this sub goal. So, but we have to first prove it. So let me prove it. We can enclose the proof script of this asserted lemma and the brackets and the brackets or curly braces. Okay, so we can continue with induction on n, and obviously we would get two. Okay, so we have just focused on the asserted lemma. This is proof within the proof, so we can now proceed with induction on n. We would get two sub goals, and we can focus on the first sub goal directly, or we can just continue with the sub goal, with the first sub goal by just simplify it. So we would get true on both sides, and we can close this sub goal with auto, and the second sub goal would appear automatically. We can also continue with simplification on the second sub goal as well, and we get this, and this we can close with inductive hypothesis. So we can either rewrite or we can apply the inductive hypothesis IHN, because the hypothesis is exactly what we have in the sub goal. So this would also be closed, and we can end this proof script, and this would give us the original sub goal that we had left. And so the original, the old or unproved sub goal is now uh, in front, so we can now target this sub goal. And but we have a very useful hypothesis in the about the line among the hypothesis. Okay, so now we can rewrite this hypothesis. We can because n is equal to true, and we have exactly the same expression here, so we can replace this highlighted part of the expression with true using rewrite tactic. So rewrite HEQ. So this highlighted text would be replaced with true. And now if we simplified, this expression would be simplified. True and the equality b, this would be simplified. And okay, so simplified. Okay, now we got this, and we have exactly the same situation in hypothesis IHL. So let me apply that hypothesis IHL, and we should be able to close this proof as well. Okay, so we store it in the repository using QED. Okay, similarly, there is another theorem on bags, which is similar to netlist. So count member non-zeros, and this is the name of the lemma theorem for all S of type bag. We say that 1 is less than or equal to count 1 in the list or bag where 1 is appended at head, and this is equal to true. Let me compile this first. True is not accepted. And why is okay, so why is this not accepted? Let me close this in parentheses, and let me close the same in parentheses as well. And okay, so okay, sorry, this is there is a question mark because this is Boolean equality. If we do not use the question mark, then this is considered as proposition, but this is a Boolean operator now. Okay, so this is now okay. Okay, so this theorem says that if count is a function that counts this number, the occurrences of this number in this list or bag, and this is S is a bag where we have 1 at the head of this bag and 1 is counted here. So we do not know if the number of occurrences of 1 in this bag is, but we know that there is at least 1 occurrence in this combined bag where 1 is appended here, where 1 is at the head of the bag. Okay, so and this count must be greater than or equal to 1. We know that it is the count or the number of occurrences of 1 in this combined bag is at least 1. We know it because 1 is already there, it's visible, and we are not sure the number of occurrences of 1 in the rest of bag, but we are at least sure that the number of occurrences 1 is at least 1 occurs at least 1 time in this bag. So we should be able to prove it. Okay, so we are in the proof mode, and as usual and true, we introduce a bag S of type bag, and then we can use induction on S. So we would have 2 cases because S is a bag, so it's is a bag, so it can be S can be null, or it can be it can be non-null. If S is null, then one at head of S would give us just a list or bag with only one element, and that is 1, while in the other case it is non-null, which is shown here. Okay, so we have two cases, two sub-goals, and we want to focus on the first sub-goal, and we can simplify it, and when we simplify it, we get both sides the same. We can close this with auto, and now we can focus on the second sub-goal, and this too can be solved using simplification. We cannot write inductive hypothesis S, but if we simplify it, we directly get the two sides the same, so we can close this with auto. And remember that we did not use the inductive hypothesis, so if we would have chosen destruct instead of S induction, let me choose destruct on S. We get two sub-goals. The first sub-goal is closed by simplification. The second sub-goal is closed by simplification as well. So it is okay if we continue either with induction or destruct. So if we do not need the inductive hypothesis, then in goals like that, we can proceed with case analysis using destruct tactic as well, just like we did here. Okay, so there is another theorem based related to the successor of natural number, because this is used in our next theorem. So let me first prove the theorem related to successors of natural number. Okay, so the theorem is less than equality Boolean n and successor of n for all n of type nat. I am not using the data type nat because the Coq system will automatically infer it. N is less than or equal to, this is Boolean less than equality Boolean successor of n, and this is true. So it says that for any n, successor of n is always greater than or equal to n, because we know, let's suppose n is 4, then successor of 4 means 5, so 5 is greater than 4 because n is 4. So this should be true. And okay, so we are let me enter it into the proof mode, and okay, so as usual we can continue using intro, so only one variable n, that is a mode to the hypothesis. And now we can use case analysis, and let me choose destructing n. So if we choose to destruct n instead of induction, let me see what problem we will face. So the first sub goal is here, and we can let me simplify it. So 1 is greater than or equal to 0, and we should get true on both sides. Yes, we get. So we can close this sub goal with auto. And let me enter into the second sub goal, and if we continue with simplification, what we will get, we got this. And if I close it auto, maybe the auto will work, but the auto doesn't work. So what, we are stuck here, and we can continue with destruct on this second n. This n is different than the first n. Okay. Okay, so we actually choose the wrong tactic here. We should have used induction, and the reason is that we actually lost the inductive hypothesis that would otherwise we get when we solve the first goal or first sub goal or the base case. So when we choose to do induction on n, we will get the same two sub goals. But when we solve the first sub goal, like here, we would get an inductive hypothesis. This is what we did not get when we used destruct instead of induction. And this inductive hypothesis is very useful. So when we continue with the second sub goal, we can apply, instead of auto, we can apply or rewrite IHN, which is the inductor hypothesis generated after the first subgoal was closed, and we were able to close this proof as well. Okay, so now this is a very simple theorem, but we need it in the next theorem, and the next theorem is theorem remove does not increase count. This name is a bit misleading. Okay, let me remove does not increase count 0. I think we should add a name 0. That removing 0 from a bag doesn't affect remove 1 remove 1 0 from a bag does not affect the number of counts. Let me put the statement of the theorem, and we can then see what this theorem says. So let for all S of bag, for all S of type bag, count the occurrences of zeros in a bag got from remove 1, which removes the first occurrence of 0 from the bag S, and then we count the occurrences of 0 in this bag is always less than or equal to the bag, the occurrences of zeros in the bag not from where no zeros have been removed, and we say that this is true. So obviously this is true. So this is a bag S. This function just counts the number of occurrences of 0 and the bag S, and but this function removes one occurrence of 0 from the bag S. So if we count the number of occurrences of zeros and this bag S from where one occurrence of 0 has been removed, and compare it with the original count of zeros in this bag, then this original would be greater than or equal to this count, and this is equal to true. So we say that this is true. This relation is true. Okay, so let me compile it, and this gives error, and the reason is that this again has a typo here. So we put question mark. So this question mark would make this operation as a Boolean less than equal Boolean. Okay, it should be accepted now. Again error. Okay, so what is the problem? Let me check. We have missed a parenthesis here as well. Let me try again. Okay, now it is accepted. Okay, so let me enter into the proof mode. We are in the proof mode, and as usual we introduce the variable S about the line into the hypothesis, and then we choose induction on the variable, the only variable S. Induction on S. S is a bag which is a list. In fact, we get into the first sub goal, and we continue with simplification. So we continue with simplification, and we get R2 true on both sides, and we can close this with R2. Good. And now we can continue with the second sub goal. And with the second sub goal, we can continue. Let me focus on the second sub goal first. We can continue with simplification, and okay, so now we have a very complicated sub goal, and here we have a number of pattern matching match with statement, and this is a bit looks complicated, but the goal is not that much complicated. So what it does that it replaces this simplification function replaces the remove one function with these match n with statement and f then else statement. So this f match n with statement actually is pattern matching on n, and we do not know the value of n. So n can either be 0 or it can be s followed by something. So if we do case analysis on n, like if we use destruct n, then we would get two subgoals. In one subgoal n would be 0, while in the other subgoal n would be s followed by something. And there's something maybe renamed as n or n prime or any other variable. It's better if we rename it so that it is renamed different than the original n. Okay, and similarly, when n is 0, this will be reduced to true, and then f true would give us then s would be the result, and similarly for the other fault as well. So let me use case analysis using tactic destruct n as, so you would get two subgoals as n is a natural number, and we would get two subgoals. In the first subgoal there is no new variable because n is replaced with either or 0. While in the second subgoal n is replaced with successor followed by something, and let me call there something in prime. Okay, so let me compile this. Destruct n as, okay, so in the first subgoal n is replaced with 0, and the 0 is simplified as well, and that gives this statement, while in the other where n is replaced with successor followed by s followed by something, that something is in prime now, and the match f then else statements were also simplified, and they give these statements or these subgoals. Now we can continue with executing these subgoals. And okay, so let me sorry, because we have already used bullet plus at this level, so now we have to use minus bullet. Okay, so I'm just going to focus on the first subgoal after using destruct n. Okay, so what we have a situation where we have a number, and we say that the number is less than or equal to successor followed by that number. So count 0s, count 0s. And we have a lemma just proved before this one, where n is less than or equal to successor followed by n. So let's assume this is n, and this says that anything looking like n is less than or equal to s followed by that n. So and n is for all n means n can be count 0 as n can be 0, n can be 1, 2, 3, 4, or it can be an expression like this of type net, and count 0 s is also a net. Okay, so we can rewrite this theorem here, and this would give us true for this expression till here. Let me rewrite it. So I would just use rewrite less than equality and Sn, and we should get true for this expression here. Yes, we get true, and we can close this with auto. Okay, so and we can now focus on the second subgoal, and in the second subgoal we have a situation where n was replaced with successor followed by n prime, and we should first think if we can rewrite this inductive hypothesis. Remember that we have true here, so this true can be replaced with this expression, but that may not be straight away, that may not take us to the subgoal in an easy way. So let me first try simplify, and if we get some familiar shape of this conclusion, then we may be able to rewrite the inductive hypothesis in a better way. Let me simplify it. Okay, so after simplification we got exactly this expression. So now if we rewrite inductive hypothesis S, and replace this term with the right hand side of the inductive hypothesis IHS, then we would be able to close this theorem. So let me rewrite from left to right. IHS. So I'm not using the arrow because by default it is from left to right. So IHS, this by reference of this hypothesis, this highlighted expression would be replaced with true. And let me compile this if it happens or not. Yes, it does. So we got true on both sides. So we can now close this with auto. Okay, so we can now close this theorem and we are done. Okay, so let me create an exercise for you, a homework for you. We have just seen that Boolean equality on list and prime, this function checks if L1 is a subset of L2 for any two lists, and this function doesn't compare if the two lists are of the same size, but it is for sure if L1 L2 this equality returns true, then the length of L2 must be greater than or equal to L1, and we have to prove this. Let me write it in form of this is a homework, and let me theorem equality Boolean list n prime length list n length and prime. Okay, so for all lists L1 and L2, I'm saying that f length f equality list and prime L1 L2 is equal to true, f is equal to true, then it implies that length of L2 L1 is less than or equal to length of L2. So what I'm saying that if L1 is a sublist of L2 using this relation, then length of L2 is greater than or equal to this is equal to true, greater than or equal to a length of L1. Let me compile this, and I think I should introduce some parentheses maybe. Let me see what this error is. The term listnat has type bool while it is going to have type nat. Okay, so equality Boolean equality of type list is equal to is equal to true. Okay, so now it is accepted. So what I'm saying that if this is this relation, I think we do not need the parentheses. Let me remove them because they're redundant. So what I'm saying here is that if L1 is a sublist of L2, then it must be the case that the length of L2 is greater than or equal to length of L1. And we should also be, if we remove this Boolean equality, we can use the propositional relation. This is the relation. So you might be used to with the Boolean equality and Boolean relation, Boolean less than equality relation, but it's better to try the proposition. Okay, so this is the homework for you, and I just admit this theorem. So it is admitted, and this is the work for you. So please try induction on L1 and try to close this theorem. Thank you.